Everybody who's here is here. That much I can say for sure. So I'll begin. Dear Heavenly Father, we thank you for this morning. Thank you for these students. I just pray that you'd help us to use the time wisely, Lord, and glorify you in what we do. In your name I pray, Lord Jesus. Amen. So guys, glad you're here. This is the homework that I had mentioned. That's the supplemental problems. So basically I'll make this due Tuesday, and I'm going to push the homework. The homework I had said was due Monday, but I'll let that be due Tuesday, so you guys have Monday still to ask me questions about it, because I get the sense that most of you haven't attempted most of those problems yet, so I might as well just kind of know what I do. Collect it on Monday. You haven't done it. What's the point, So I will collect it on Tuesday. Hopefully it will be less pointless. But I would encourage you not to wait till Monday to do those. We only have so much time Monday, so I'll try to help you, but there's only so much I can do in a finite amount of time. Now, I guess I will have to post this for those people who are not here. Give it to him Monday, say it's due tomorrow? Tell you what, since you guys are here, let me just work a couple problems, some additional examples. So my example number one, if I have a vector A, which is like 3, 7, and if I have a vector B, which is say -1, 1, the question is to calculate what's the length of A, what's the length of B, and what's the angle between them, all right? So the length of A is the square root of 3 squared plus 7 squared, also known as what? Nine plus 49 is square root of what? 58? Okay, it's the square root of 2. Now what's A dot B? A dot B is equal to, let's see here, 3 times -1 plus 7 times 1. You take basically you just multiply the matching x components and the matching y components and add them together. This is the dot product. We defined it the other day, but there it is again. For this particular pair of vectors, that's equal to 4, right? So what I'm doing right now is I'm calculating the length of each vector, the dot product, and then I'm going to use the theorem I stated about the dot products to calculate the angle between them. So what do we know? The theorem says that, and I advertised you guys, this is essentially the law of cosines written in this formalism, but A dot B is equal to A, B cosine of the angle between, all right? So I get cosine of theta is equal to 4 over the length AB, which is what? Square root of 2 times square root of, well, I guess square root of 58 times square root of 2. Which you could simplify, but I'll just do it. So theta is equal to inverse cosine of, anyway, we're going to have to plug it in the calculator. 2 times 58 is 116, right? So a little bit less calculator work if I do that. Okay, I get 68.2 degrees, roughly speaking. There you go. This is so basically this is, let's see here. So here's roughly speaking the picture. This is B. A is something like 3 over 7 up, which is something like that. I don't know. And we just figured out this angle here is 68.2 degrees. Right? No protractor required. So this is just a showcase of what the dot product does for you in terms of geometry, okay?
We're putting stuff like this into degrees now, right?
You could use radians if you wanted. I'd be fine either way. Yeah, I mean, you should say degrees if it's degrees and radians if it's radians. Now, if we're doing calculus, we'll probably be, if we're differentiating like sine or cosine, we're assuming radian measure. Otherwise, it's ugly. All right, yeah, okay, so the dot product was by definition. So if this is A1, A2 dot B1, B2, it's A1, B1 plus A2, B2. That's it. AB cosine theta. Yeah. Here's an example. If we take the time derivative of f times a, where a is a vector, so here, function of time, and let's suppose a, which is a1, a2, is also, these are also functions of time. All right, so I'm differentiating a product of a function times a vector of functions. Then I stated a property the other day. I stated properties of these for you guys, remember? Let's just see how to prove one of those. It's pretty simple. It gives us a little bit more experience with what we're doing here, maybe a little bit more understanding. So this is ddt of, what is f times a? This is fa1, comma, fa2. All right. How do we differentiate a path? We differentiate it one component at a time. So this is ddt of fa1, comma, ddt of fa2 all right, and okay, so how do you differentiate those? F and A1 are both just functions of time, right? You guys know? Product of functions use the product rule, right? So we do product rule 2 times. What do you get? All right, so it looks like we've got 2 different kinds of terms, right? We've got the ones with derivatives of f, and we got the ones that have no derivatives of f, right? So the derivative of f terms, there's 2 of them, these guys. So you can rewrite this as one vector, df dt, a1, comma, df dt, a2, plus the other terms, using the how we add vectors rule. This is an allowed algebraic step, okay? But now how do we scale or multiply vectors? Like, so for example, if I had gone back over here and I did something like 5 times 3, 7, what would that be? The way it works is I do 15, comma, 5 times 7, 35. You just multiply each one. But you can also do you can also undo that, right? So like I've got a common df dt factor here and here, right? I can pull it out. What does that give me? That gives me df dt times a1, a2. And over here I've got a common factor of f, right? But what do we have then? This is exactly just the vector a again, right? So I have df dt times a plus f times dA dt. That's one of the properties of the derivative of paths and functions and such that I mentioned for you guys the other day. That's how you prove it. Not a big deal, really. It's just ordinary product rule plus the rules of addition, vectors, and scalar multiplication of vectors. But you just do one component at a time. That's it. Now, one of the problems, the reason I'm showing you this is the proof for problem 6 in the homework I just gave you is kind of similar. See problem 6 in the supplemental thing? If you look at that, I ask you to show the product rule for the dot product. It's not exactly the same, but it's kind of a similar calculation. Let's see here. Okay, let me do another example. Unless there's a question. So another example, what if we had r of t equals to, let's say, sine of t squared, comma, e to the cosine of t plus t. Here's the question, find the velocity, acceleration, and colliding tangent line at time equals to what? You guys pick the time. 3. Okay, I'll take that. Very good, very good. You're going to say that. That's funny. All right, so basically here we just have to go, okay, what is the velocity? Velocity is dr dt, right? So we have to do what? d dt of the sine of t squared, comma, d dt of e to the cosine of t plus t. What is that? Chain rule, right? So I've got 2t cosine of t squared. And over here I've got minus sine t e to the cosine of t plus 1. So there you go. There's the velocity at time t. What's the acceleration at time t? Actually, before I do the acceleration at time t, now's a good time to do the colliding tangent line. So we use the velocity to find the colliding tangent line, right? L of t is what? L of t will be equal to r of 3 plus t minus 3 times v of 3. So I didn't write that as velocity when we talked about it previously, but it is, right? dr dt is velocity, so the equation for the tangent line, the direction vector for the tangent line is given by the velocity at the appropriate time. It's important that you evaluate the velocity at the appropriate time. Okay? Like you shouldn't just put v of t there. That would be wrong. But also a very popular mistake. Very, very popular. Both in Calculus 1 and in here. So, anyway, so you guys stuck me with the number 3. So it looks like I'm stuck with a sine of 9, comma, e to the cosine of 3 plus 3. Couldn't have made it pi. No, got to give me 3. I know I did give you freedom, and with that freedom comes responsibility for me. So yeah, freedom does come with a price, yes. Let's see here, t minus 3. Where are we? Okay, so I got to plug in 3 into this blue thing right here, right? It ain't pleasant, but here it is. 6 cosine of 9, comma, minus the sine of 3 e to the cosine of 3 plus 1. That is the parameterization of the tangent line, and I think that's a perfectly fine answer. All right. You don't have to collect terms and multiply it out if you don't want to in that problem. Right. Sometimes it's instructive to collect all the terms together and stuff, but this is a legitimate answer right there. Yeah. What's the acceleration then? So this is the parameterization of the colliding tangent line, right? Why is it called the colliding tangent line? That's a new terminology. I've invented that this semester. Previous semesters, I always had this confusing interchange between students like, do you want the tangent line which is parametrized so that it's centered at the point, or do you just don't care? So my way of saying I care is I want the colliding tangent line. That makes the parameter of the tangent line and the parameter of the curve match up at the point of tangency, right? T is shared by both the path and the tangent line here. It's the same T, so to speak, in the sense that when you put T equals to 3, we get R of 3, right? So like, this is in no way, so like here's L of T, and then here's R of T. This is just a totally heuristic picture. I have no idea what direction that tangent line is actually pointing. I haven't even thought about what's the sign of the direction vector or anything. I'm pretty sure that's wrong because I think I don't know. Who cares? Anyway, what I'm trying to say is this vector might point this way or that way. I'm not sure without thinking about the numbers there. What's the acceleration? Let's get to it. Acceleration is a little bit unpleasant here. dv dt. So what do I have to do? I have to take d dt of 2t cosine t squared, comma, d dt of minus sine t e to the cosine t, like so. And so I got two product rules to do, right? I got 2 cosine t squared minus 4t squared sine t squared. And over here I've got minus cosine t e to the cosine t plus sine squared t e to the cosine t. And there you have it. That's the acceleration at time t. I mean, if we're just talking about a single particle, right? If you think about F equals ma, the force as a function of time on this particle is pretty weird. It's like, I don't know, it would take a kind of bizarre force to create this motion. Anyway, I hope you see that this is not a mean question. It's just you got to differentiate to find the velocity. You plug in the time and use the colliding tangent line setup to find the parameterization of the tangent line, and then the acceleration we get from differentiating 2 times. It's not a bad thing, right? What if I wanted to set up the arc length integral? What would I need to do here? If I said, what's the arc length from time 0 to time 3, what would it be? I would do to integrate from 0 to 3 of the speed, right? But that is actually the integral from 0 to 3 of the square root of what? We got it right here. We just have to square these things. So 4t squared cosine squared of t squared plus this stuff, 1 minus sine t e to the cosine t, right? Quantity squared. This is what is called, this is an integral. How can I'm forgetting the terminology. It's an integral answer, right? It's not, it's the arc length up to an integration, I guess you could say. That's not the standard terminology. Dang it. What is that called? Oh. This is an integral solution for the arc length, yeah. Or sometimes people will say something like up to an integral. But that's not an integral I can do, right? But numerically, we have methods for calculating integrals, so that gives you a prescription how to calculate the arc length, given everything else here. Let me work another problem for you that's kind of based on the homework I've just given you. But it's a little bit kind of off the beaten path in terms of our other discussions so far. Let's see here. Suppose r of t is equal to 1 comma t. And let's also suppose, oh, I'm sorry, not r. I want to make that the acceleration. Suppose you're given the acceleration is 1 comma t. And you're given that the path you're looking for has position 1, 2 at time 0. And you have velocity at time 0 of, I don't know, 6, 7. Find the path. Find path with this data. This is different than the question I just asked because the question I just asked, I started you with the position or the parameterization of the path, right? And then I said, find the velocity and acceleration. This is the opposite question. I'm giving you the acceleration, asking you to find the position. So here we have to do something called what? So we've got A is dv dt, right? How do you solve for v? What's this process? Yeah, integration. So how do you integrate? Well, you just integrate component by component, basically. So this tells me v of t is equal to some constant vector. I don't know what it is yet. Plus, well, t integrates to what? Integral of 1 is what? What can I differentiate and get back 1? T, right? What can I differentiate and get back t? T squared over 2, right? Yeah, 1/2 t squared. So there's the velocity up to a constant vector. How do I figure out what the constant vector is? Well, I was given an initial velocity, right? So now I use that. But v of 0 was given to be 6, 7, right? So 6, 7 is equal to c plus 0, 0, because if I plug in times 0, I get that. So what's that say? It says my constant vector of integration was actually 6, 7, and that gives me, finally, the velocity as a function of time is, and here I think it's helpful to bring stuff together, 6 plus t, 7 plus 1/2 t squared. So there's part of the answer. There's the velocity as a function of time. By the way, if I asked you to calculate the arc length of this path, we could do that now, right? For example, the arc length function, what would the arc length function be? Arc length function, I could do s of t as the integral from like 0 to t of the square root of 6 plus u squared plus parentheses 7 plus 1/2 u squared du. If I was so inclined, there you go. That's the arc length function. We talked about that in our previous lectures, but just throwing it out there. I didn't ask you about that in the homework set, right? But you shouldn't think about this homework set as being disconnected from what we did in chapter 10 either. Okay. Okay, so anyway, what's next on our list? I'm supposed to find the path, right? Actually, I should have added onto this also find the velocity. I mean, I kind of have to find the velocity on my way to finding r of t anyway. So the path, find the path. What I mean by that is find r of t, right? Okay, so we have everything we need to do that. We have that v is equal to dr dt. That's by definition, right? And on the other hand, it's 6 plus t, 7 plus 1/2 t squared. Sorry about this scary comment here. This really has nothing to do with this problem. I was just doing some mathematical sightseeing. You can ignore it if you want. right? You know, I have this vice. I like to stop and count the roses. Let's see here. So R of t is what? Integrate, right? What's the integral of 6 plus t? I get 6t plus 1/2 t squared plus some constant, let's say b1. And then what's the other one? I get 7t plus 1/6, because 1/2 times 1/3 is 1/6, t cubed plus b2. So you have options, right, guys? You can either add a constant vector out here like that if you prefer, or you can just add constants, different constants in each component. It's equivalent. Like if I erase this b1 and b2, I could write like plus b vector out here and it would be the same thing. These are flavor choices you have. Now, we know something else. We know that r of 0 is what? 1 comma 2. But it's also plugging in times 0 into this expression up here. It's also b1, b2, right? So there you go. The position, the path that we're looking for, r of t, is exactly 6t plus 1/2 t squared plus 1 comma 7t plus 1/6 t cubed plus 2. Now, do you have, any of you guys have the strong sense that you're in reruns right now? I mean, you should have a strong sense of deja vu from what we're doing, because this is exactly what we did in Calculus 1 when we discussed velocity and position in one dimension, right? What's the difference? Two components, right? That's the difference. And we can think about other issues, right? Like arc length. This was kind of boring. In one dimension, this was the distance traveled. It's just integrate the absolute value of the velocity, right? Speed is absolute value of the velocity in one dimension, because like when you just have one thing squared, you got the square root of something squared, which is just the absolute value. So like the distance integral just simplifies integral of absolute value in one dimension. I tend to think that's more confusing, though. I don't know, personally. I guess that's pretty much. Well, I mean, there's two other types of questions on here which I should address. So I'll do that. But any questions about? Here, we do it over here. I rarely use this board, and this is just kind of, we've done entry-level problems already with what I'm about to do, but this is just kind of like the next level of sophistication for these problems. So suppose you've got something like x squared plus 6x plus y squared equals to 3. Parameterize this curve for y less than 0 in, well, if I had more time to make this problem and think through it, I would put a thing in there. I'm going to have to I'm going to have to finish the statement of the problem as we work it out, if you don't mind. Let me just think about it for a second. Yeah, counterclockwise direction. Or I could say also something like parameterize this curve for y greater than 0 such that it goes to the, let me think about this, right, I believe. I could do something like that. That might be less sort of giving it away. I think if I write counterclockwise direction, you kind of probably already have a sense it's some kind of closed loop, right? I probably wouldn't use the terminology counterclockwise direction if it was part of a hyperbola, you know? Okay, so here's what we do. Complete the square. So I've got x plus 3 quantity squared, right? So I do x plus 6x plus y squared is equal to x plus 3 squared. But if you look at that, what did I just do? I added 9, right? Subtract 9 plus y squared equals to 3. So that implies x plus 3 quantity squared plus y squared is equal to 12. Tell you what, this problem's a little bit too easy. I want to make it slightly uglier. Let me just add a number to make our life less easy. I don't want to misrepresent what I expect from you guys. So you put any number you like here. Like we could put 7. Let's just make it just ugly, 7. What does that do? Well, it puts a 7 here, right? Oh, I guess it was still, yeah, fine, that's optimal ugliness. So look here, then what I do with this is I look at this as, well, what I'm really looking at is x plus 3 quantity squared divided by 12, right? Plus y squared divided by 12 sevenths equals to 1. And so my thinking is what? I mean, we know a trig identity, right? Cosine squared plus sine squared is equal to 1, right? So if I can make the things that I've just written a cosine squared and a sine squared, then I know it'll work, right? You could say that this is just a slight twist on the parametrized circles we did before, parametrized ellipse example we did before, right? So essentially what this tells me is that what I should do is I should let x plus 3 divided by the square root of 12, I should make that like a cosine, maybe cosine t, and I should let y divided by the square root of 12 over 7 be something like sine t. I'm pretty sure that if I do that, that gives the curve a counterclockwise direction, because the usual sine cosine parameterization is counterclockwise. And so then I solve for x, like x is equal to minus 3 plus the square root of 12 cosine t, and y is equal to the square root of 12 divided by 7 sine t. And those are parametric equations for this curve, right? So I can draw a picture. This is an ellipse centered where at minus 3 comma 0, right? And which is it longer? Is it longer in the x direction or the y direction? Which has which the semi-major, which is the semi-minor axis here for this ellipse? I mean, 12 is bigger than 12 sevenths, right? So that means it's longer in the x direction, right? So like this is like x squared over a squared plus y squared over b squared, right? Like that. So I'm thinking, so basically, what's the square root of 12? It's a little bit bigger than 3, right? So this goes out to here and out to here, something like that. 12 over 7 is what? It's 1.4-ish. Square root of that is what? Not too big, right? It's something like here. So the that would be the whole ellipse, something along those lines, right? The center is where? Again, minus 3, 0. Now what I said to parameterize this curve for y less than 0 in the counterclockwise direction. Do I have counterclockwise to start with? Like this right here would be what? This is t equals to 0, right? If you plug in t equal to 0 into that, you get minus 3 plus root 12, which is here. And then, well, that's comma 0, right? So that's its, let's say, starting point for t equal to 0. And then this point would be what? This point actually up here would be t equals to pi over 2 for what it's worth. Right? Try that out. If I put t equals to pi over 2, I get x equals to minus 3. And this is square root of 12 over 7, right? So you can see, in fact, if I can add an arrow to this. The path is going this direction, right? So it is, in fact, going counterclockwise like I want, right? What if you write down equations and it goes clockwise? What do? It's really simple. You just change t to minus t. That will reverse the direction of the curve if you chose badly to start with, okay? So then what? What? Just to complete the thought, the parameterization is not complete without a choice of the domain of the parameter, right? So this is part of the answer, but I have to add where what? T is between what and what? You guys tell me. I want y less than 0. Let me graph it. So that's this part of the curve, right? I mean, fill in the, I guess it depends on, oh, I said less than 0. I didn't include 0, so my picture is actually, I do mean the circles at the end, yeah. Okay. You guys tell me, what should I fill in the blanks? Yeah, pi to 2 pi will work. Certainly. Pi less than or equal to t less than or equal to 2 pi is one choice. So, yeah, we'd start here and go over to there. I think you could also do. Yeah. Oh, thank you. Very good. How would this have changed? If I had said instead of y less than 0, what if I had said y greater than 0? You would have just done what? 0 to pi, natural choice, yeah. Well, I hope that is enough to give you a good, solid start on the homework I just gave you guys, the handout, right? Do you guys have questions about something in the book? We still have time left, so. Let me find a good problem for us to chew on here in the last few minutes. See, we're looking at, typo. R equals 2 cosine theta, and R equals cosine theta, and the raised theta equals 0, and theta equals to pi over 4. It's number 9 from section 10.4. So we've got R equals to cosine 2 theta, or wait a minute. 2 cosine theta. That's very different. That 2 inside or outside makes a big difference. So R equals 2 cosine theta, and R is equal to sine theta. Good grief. R is equal to cosine theta, as well as the raised theta equals to 0, and theta equals to pi over 4. Find area. Find the area bounded by these dudes. This is section 10.4, number 9. Oh no, that is a leftover from a previous discussion. Sorry about that. So I guess when you're calculating area, first thing you need to do is figure out what it looks like, right? And so this here, let's see here. So here's theta equals to 0 is this guy, right? Theta equals to pi over 4 is this one, right? R equals to cosine theta, what is that? It's the unit circle. Well, here, let me do that one in red. I think we might be able to figure it out by just plugging in points. This one, right? You say put theta equal to 0, what do you get? R equal to 1. Put theta equals to pi over 4, you get R equals to what? 1 square root of 2. Yeah, so it's like, if you put theta equals to pi over 2, what do you get? 0. I bet this is this circle, right? And you can verify that, right, by just multiplying. You got r squared is equal to r cosine theta, right, which is equal to x. So this gives you x squared plus y squared is equal to x, which gives you x plus 1/2 squared plus y squared is equal to 1/4, which is in fact this circle centered at. You're right, it's a circle. Now the part that's relevant to us really is just this piece right here, right? That's the piece that's between the rays we're interested in. Now how about the 2 cosine theta? What's that look like? Oh, it's the same thing, just, well, no. How should I think about this? I would like to think about it in green. Oh. This is not helpful. I guess we'll be doing it in black. So theta equals to 0. It starts me out here, right? I start here. When I get to pi over 4, I'm to like out here. So that would be like r equals to 2 over root 2, right? When you get to theta equals to, yeah, I think this is also it's a circle, but it's, I'm not sure what it looks like exactly, but it's, I think it's a bigger circle. Yeah, this gives me x squared plus y squared equals to 2x, which gives me x minus 1 quantity squared plus y squared equals to 1. Just being quick, sorry, we're almost time. So that actually has center. That's circle centered here. All right, so that's enough. We can now see that the area we're looking for is this one, right? So to find that area, what do I do? 1/2 integral from 0 to pi over 4, r out squared minus r in squared. R out squared is 4 cosine squared theta, minus r in squared is cosine squared theta, d theta. And so we just need 3/2 the integral from 0 to pi over 4 of cosine squared theta, d theta, whatever that integrates to, that's the area. So that's actually 3/4 the integral from 0 to pi over 4, 1 plus cosine of 2 theta. That becomes, oh, I guess I can't ignore anything there. So I get 3/4 theta plus 1/2 sine 2 theta. Evaluate from 0 to pi over 4, what do we get? I get 3/4 plus pi over 4 plus 1/2. I guess you could simplify that a little bit, but that's what I get. Well, I started class like 6 minutes late today. I ended it 2 minutes early. I think I still owe you guys 4 minutes. Is that accurate? No, I owe you 8 minutes? Wait. How's that work? Oh, so it counts against me whether I go after or I start late. They both count against me, huh? All right. Fine. Where was I? This is section 10 point what? 4, number 9. We get 3/16 pi plus 3/8, which is indeed what we got. Woohoo! So either we're both wrong or the book and us were both right. But that's how you think about this kind of problem. First of all, graph it. Second of all, we use 1/2 r out squared minus r in squared, or integrated over d theta. That gives us the area, as I tried to motivate some other day. Yep.
I have a question about 25 in the same section.
Uh-huh.
I just don't understand what it means by like the interior of like how would like this phrase it work?
Interior to both r equals 1 minus sine theta and r equals sine theta. You guys can go if you want to. I'll just talk to him about it. If you need to go now, it's cool. But I can solve it. We got time. You can leave the camera. Just put the camera over here and leave it on. I'll turn it off if you need to go. It's cool. So you want to know about this one?
Well, like
Inside.
I grabbed both of it. Because you're supposed to set up the integral, you're not supposed to solve it. So
Right.
I wasn't sure what it meant, like what area was actually wanted me to find when it said the interior both.
Well, it means you got to set up the integral. I mean, I don't know. I need to think about this to understand what it means by inside both. I mean, you know. Let's see here. Let me try to double check on it. So this guy, I can multiply by r, right? That's easy. Then I can complete the square. That's x squared plus y squared equals to y. So this gives me x squared plus y plus 1/2, minus 1/2 rather, squared equals to 1/4. So that's one of them is the circle here, right? That's the r is equal to sine theta. That's that one. Then you've got this thing. Well, I guess my I guess I got to go back to basic graphing here. I don't think I have much of a choice. 1 minus sine theta. So minus sine theta looks like this, right? So 1 minus sine theta is just that shifted up.
It's like one of those cardioid.
Right, yeah.
Yeah.
Let's see here. So it's at going from 0 to pi, to what is it? This is pi over 2. We go from at 0 it's at 1. At pi over 2 it's 0 again. So it's doing that, right? And then going from here to here, that would be what? That's 3 pi over 2, right? 3 pi over 2. 3 pi over 2 is, where is that? So oh, okay, yeah, that's a good idea. So, okay, so at pi, so it's like that, right? 2. And then like that. So it's one of these guys.
Yeah.
So they said find the area inside those, right?
Yeah.
So that's two things. That's this and that.
Well, that's what I did, and my answer, I couldn't seem to get. Yeah. What they have in the back of the book is very interesting.
Yeah, it takes like 3 integrals.
Are they like adding some integrals? I don't know what.
What was this number? Was this again?
25.
It's you have to follow the line as it goes along, so it takes 3 integrals to the area. Yeah. Huh? Well, there's an example problem in the book. I think it's like the 4th example or something. There's one very similar to it.
That's another question about it because I did it, and that's why that's kind of the graph I drew in the area I assume they were talking about, and what I got was not even close to what they have in the back of the book.
Okay, so I mean, once I have that, I have to decide what's our in and our out, you know? And so that's, man, see, that's, see, I'm not sure. I don't think I've done one like this before because the radius function, the inner and outer, I mean, like if you draw, oh, no. So I can sometimes convince myself that this is giving the inner and outer radius, but I'm just being stupid. So it should be like this, right? So this is pi over 4, right?
Yeah.
So I would say it's so we would have the integral from 0 to pi over 4. And then, so this is which one? This is the that one, right? So I have 1/2 that, 1 minus sine theta, quantity squared d theta. That will give me nothing more than this area right here. Then plus the integral from 0 to pi over 4 of this guy, which would be sine squared theta divided by 2 d theta. That would give me this area, because the outer radius is given by that. And then I would argue by symmetry, you just double this personally. That's how I do it. Let me look at this is odd.
Yeah, it's
One thing I'll note, they intersect at 5 per 6.
Oh, well that will be part of my trouble understanding the answer then. 10 point, what was it? 10.4? Yeah, it's just this, but with pi over 6 instead of pi over 4.
Okay.
So the issue is you have to like just focus in on what's going on here, right? So the key to understanding is to draw a ray out from the origin, right? And whatever you hit is your outer radius, right? But the thing is, this and that are different functions. Like here, our out is sine theta. Oh, excuse me. 1 minus sine theta, right? And this is sine theta. And the dividing line between those, pi over 6, and that's why you have to have two integrals. And Thomas, you said this was like example 4?
Yes.
Yeah.
Example 4 is like identical except with an extra 2 or something.
Aha. Mm-hmm.
That integral, like the second one, it must be from pi over 2 to, like, from pi over 6 over pi over 2.
Oh, I set up the integral wrong. Yes, this one should be. Wait a minute, no. This one?
The second one. Yes.
Uh,
No,
No, the first one would be pi over 6 to pi over 2.
yeah. Thank you. I'm still not quite right. Sorry about that. Yeah.
See how that works out. Let me help. Okay.
Yeah. Thank you.
Because
Oh, I will be back.